Hi, and welcome to 8.4 Kinetic Energy. This homework assignment is a little bit different. I ask you to read an outline in your textbook, page 164 to 168. Actually read it, actually take a few notes, and then you're ready to answer questions numbers 1 through 5 on page 166, which is right here. I'm going to answer these questions in a little bit. But first I'd like to derive the kinetic energy equation. I didn't have time to do it in class, so I'm going to do that first. I'm going to go over here to this blank page and I'll derive the equation quickly here. If you want to skip this part, just scroll through until I get back to that previous document and I start answering the questions. All right, so what do we have? Let's assume we have a box and we want to do some work on the box. We want to get it to move, so we exert a force. Okay, now the box is moving, and if you read the textbook, you know that anytime something's moving, it has kinetic energy. So we're increasing the kinetic energy of the box as we move along. So we have like the initial situation, and we have the final situation here. Okay, so it starts at rest. VI is 0 meters per second, and then now it has some final velocity. Okay, whatever it is. Could be anything. So that's the situation. Now, what did we do in order to give that block some velocity, to give that block some kinetic energy? We had to do some work. Okay, so work is equal to the force times the distance. We traveled some distance here. Okay, oh man. Okay. So let's look at what we have. We have a force times the distance. Well, what is force? You'll remember from Newton's second law that the force is equal to the mass times the acceleration. So we're deriving a formula. This is the first secondary formula that we're using. Let's plug in ma every time we see force. Now we're mad. Okay, we have the mass times the acceleration times the displacement. Is the same formula. Now, MA, that should look familiar. AD. Let's look at the AD portion. Where the heck have we seen that before? Here's the second secondary equation. If you look back in the kinematics section, we have VF squared is equal to VI squared plus 2AD. There's the AD. Let's solve for AD over here and plug in that stuff into this equation now. So that's how you derive equations. You just figure out what one thing is equal and plug it into the next spot. So you have VF squared minus VI squared is equal to 2AD. So we're not done yet. We have to divide both sides by 2. And we see that AD is equal to VF squared minus VI squared divided by 2. Now this might be, it might be hard to visualize what this equation represents, but we derived it way back when, and we know that it actually makes sense. So now we're plugging it in over there anytime we see an AD. So now we have work is equal to the mass times VF squared minus VI squared divided by 2. We can rewrite that as the mass times VF squared divided by 2 minus VI squared divided by 2. Now we can distribute. The work is equal to the mass times VF squared, divided by 2 minus VI squared divided by 2 times the mass. But that doesn't matter because what is VI? VI is 0 in this case. So we'll cross that out because that's 0. So now we have an equation that says that the work is equal to, well, this is divided by 2, right? So we could just do 1/2 times the mass times the velocity squared. And the work done is equal to the change in the kinetic energy. So therefore, the kinetic energy is equal to 1/2 mv squared. Very good. Just as an aside, I did mention that the work done is equal to the change in the kinetic energy. So that's called the kinetic energy theorem. However much work you're doing on an object, it'll increase that kinetic energy by this amount. So that's basically the derivation right there. That's how we get this guy. All right, let's go back to the homework. Here we go. If you skipped the derivation, you missed a lot of fun, but now let's do number 1. It says, calculate the speed of a 8 times 10 to the 4 kilogram airliner with a kinetic energy of 1.1 times 10 to the 9 joules. So we have an airliner. The mass, it's pretty massive. It's 8 times 10 to the 4 kilograms. And the kinetic energy is 1.1 times 10 to the 9 joules. And they're asking, how fast is it going? What is the speed? What is the velocity? So there's our givens, there's our unknown. The equation is Ke is equal to 1/2 mv squared. Now they're telling you what the kinetic energy is. So we could just write that in. 1.1 times 10 to the 9 is equal to 1/2 times 8 times 10 to the 4 times v squared. So now we just do 1.1 times 10 to the 9. 1/2 of 8 times 10 to the 4 is 4 times 10 to the 4 times v squared. So we just divide both sides by 4 times 10 to the 4. And you get v squared is equal to 2.75 times 10 to the 4. Make sure you're either putting these numbers in parentheses in your calculator or you're using the E button. So it would be 1.1 E9 and 4E4 if you're plugging it in that way in your calculator. And then you take the square root of that number and you get 165.8 or 166 meters per second. That's how fast this airliner is going. Okay. Number 2 says, what is the speed of a 0.145 kilogram baseball if its kinetic energy is 109 joules? This is basically like the same question, but the numbers are a little bit easier to work with. We have 0.145 kilograms, and we have the kinetic energy is 109 joules. What is the speed of this baseball? The equation, Ke is equal to 1/2 mv squared. They tell you this is 109 joules. They tell you the mass. And you're looking for the velocity again. So 1/2 of 0.145 is 0.0725 times v squared. So v squared is equal to 109 divided by that decimal. And just so you know, like, you can do this. I don't know if you know it. You could do 109 divided by second answer is where the minus sign is on your calculator. Let's see if I could actually show it in the screen here. Okay, I'll do it one more time. So 109 divided by second answer. It's instead of retyping the number, that's a useful trick. All right, so you get 1503. 1503, and now we take the square root of that. Again, you could do second square root, second answer instead of retyping this number. And then you get the benefit of, you don't have to round. You're taking the square root of whatever's in the calculator of that big long decimal. So your answer is more precise. So you should get 38.8 meters per second. All right, the more you know. You got to know how to use those calculators. That's the benefit of using the actual calculator instead of your phone. Okay, number 3. 2 bullets have masses of 3 grams. So bullet 1 is 3 grams and bullet 2 is 6 grams, respectively. Both are fired with a speed of 40 meters per second. So for both 1 and 2, it's 40 meters per second. Which bullet has more kinetic energy? What is their ratio of their kinetic energies? Interesting. So they're looking for the most kinetic energy, greatest Ke, and they want a ratio of one to the other. We could solve. I'll probably show you how to solve both, but there's a way to do it by just looking at the formulas. Okay, so before we solve, we want to use Ke is equal to 1/2 mv squared for the first bullet. Before we plug that in, look at bullet 1. It's 3 grams. 3 grams we want to put it into kilograms. So you set up your conversion factor. We want grams on the bottom here so that they cancel out. They have to be on opposite sides of the division side. And then we want to go into kilograms. You look in your reference table, and it tells you that 1 kilogram is equal to 10 to the third grams. The benefit of setting it up this way is that you don't have to guess. A lot of times people see this, they're like, okay, 3 grams, and I want to go to kilograms. Do I multiply by 1,000 or do I divide by 1,000? You have a 50-50 shot of getting it wrong. If you do it this way, this will work every single time for anything that you want to convert. It's foolproof. So you end up dividing 3 times 1 divided by 1,000. So you get 0.003 kilograms. The other way to do it, there is a shortcut. You could go 1, 2, 3 decimal places. But how do you know? Do I move it to the left or to the right? It takes some practice. You have to think about it. Does it make more sense to have 3,000? Think about it. Is 3,000 kilograms equal to 3 grams? 3,000 really massive things. Is that equal to 3 grams? No, they're not equal to each other. But think about this. If you went the other way with the decimal point, you have 0.003 kilograms. You have a small amount of really massive things is equal to a decent amount of really small things. You want the quantities to be equal to each other. Anyway, I'm getting a little off track here. So we have KE is equal to 1/2 0.003 times 40 squared. We have to be in kilograms because we want the units to agree with each other. We can't just have anything. You do the math and that gives you 2.4 joules. That's for the kinetic energy of the first bullet. For the kinetic energy of the second bullet, it looks very similar. The only difference is that we're going 0.006 kilograms because you have to move the decimal point. You divide by 1,000. You have to change the grams to kilograms. And we know what the velocity is. It's 40 squared. So that gives you a kinetic energy of 4.8 joules. Okay, so we know this and we know this. The kinetic energy of the first bullet, kinetic energy of the second bullet. Hopefully you were able to predict which one is the greatest kinetic energy. It's going to be bullet 2. All right. Not only did we calculate it, that's 4.8 joules as opposed to 2.4, but you should be able to tell right away. Bullet 2 is more massive than bullet 1, so it's going to have more kinetic energy. Well, how do you know that? Because of the equation. And that'll help you with the ratio. Now, we could make a ratio ourselves, okay? The kinetic energy of 1 to kinetic energy of 2. You could write it like this. You could just write 2.4 joules to 4.8 joules. That is perfectly fine. And then you could reduce that down, divide both sides by 2.4, and you get a ratio of 1 to 2. You could also think of it this way. 2.4 divided by 4.8. That's going to be a ratio of, again, 1 to 2. I apologize, my computer seems to be a little bit slow, so it's like making my pen wavy sometimes, but that's the ratio. Okay, and so I like 1 to 2 written like that personally. There is a way to do this without having to do the calculation above. It's just by looking at the kinetic energy formula. If I double the mass, that's what I did, right? 0.003 to 0.006, I'm doubling the mass. The kinetic energy is going to double because it's a direct relationship. Mass to the kinetic energy is direct. This problem could have been a little bit tougher if it was the same mass but a different velocity, because the velocity to kinetic energy, that's an exponential relationship because it's squared. So if you double the velocity, it's going to be 4 times as big for the kinetic energy because it's 2 squared. And then it could be even tougher if they say, okay, it's double the mass and the other bullet is going twice as fast. Then you have 2 times 2 squared, so 2 times 4, you would have 8 times as much kinetic energy. But that's not what the question asks. It just says for a bullet that is twice as massive. So again, you could see if you're doubling it, the ratio is 1 to 2, and bullet 2 has more kinetic energy. Okay, this video is already 15 minutes long. Let's see, number 4. 2 3-gram bullets are fired with speeds of 40 meters per second and 80 meters per second, respectively. What are their kinetic energies? Which bullet has more kinetic energy, and what is their ratio? That's like what we just talked about. So the mass of the bullets, they're both the same, is 3 grams, which we said was 0.003 kilograms. And the velocity of the first one is 40 meters per second. The velocity of the second one is 80 meters per second. And they want to know what the kinetic energy of each one is. Okay, so they're making you calculate each one. 1/2 mv squared, 1/2 0.003 times 40 squared. So the kinetic energy of bullet 1 is 2.4 joules. Okay, same as the question above. And the reason they're doing that is they're kind of scaffolding your thought process here. So for the kinetic energy of the second one, unlike in the previous problem, it's the same mass, but it's double the velocity now. See how they're scaffolding your thing? Oh, I forgot to write the equation. So this is for the second velocity. This previous one was for the first velocity. Again, in number 4, the velocities are the variable that's changing. So you get a kinetic energy of, well, you should be able to predict it, because if we're doubling the velocity, that means that, so that we're doubling the velocity here, it's 2 squared. So whatever you do on one side of the equation, you have to do to the other side, 2 squared, or 4 times as big. So this should be 4 times as big. And it is. It's 9.6 joules. 2.4 times 4. Anyway, the next part of the question says which bullet has more kinetic energy. That's going to be bullet 2. And the ratio, you could set it up again. 2.4 to 9.6. It's a ratio of 1 to 4, or you could rewrite it 1 to 4. Bullet 1 to bullet 2. The ratio is 1 to 4 in terms of their kinetic energy, again, because the velocity is squared. It's an exponential relationship between the velocity and the kinetic energy, as opposed to the direct relationship between the mass and the kinetic energy. Number 5, final problem. A car has a kinetic energy of 4.32 times 10 to the 5th joules when traveling at a speed of 23 meters per second. What is its mass? So let's write down the givens. In this case, they're looking for the mass. So we could write down the equation. Ke is equal to 1/2 mv squared. So the Ke, the kinetic energy, is equal to 1. Oh no, you know what the kinetic energy is. It is 4.32 times 10 to the 5th is equal to 1/2 mass times 23 squared. So now you have 4.32 times 10 to the 5th is equal to 1/2 times 23 squared. So, I mean, I could write it out. So 23 squared is 529. Half of that is 264.5 times the mass. And you divide both sides by 264.5, and you get a mass of 1,633 kilograms. And I believe that's it. Yep, have a good day.